In the lecture today, I will introduce some mathematical prerequisites. They are very important for you to understand the rest of the materials in this class. There are three topics in this lecture: matrix algebra, elements of calculus, and probability and statistics. I will introduce some fundamental knowledge of each topic and give you some reading materials. First, for matrix algebra, the first question we have to answer is what is matrix algebra? It's actually a kind of calculation upon arrays of numbers or data. We know that in transpose system, most data sets are matrix type, and we do a lot of calculations based on matrix. It's very important for us to know how the matrices are calculated or operated in transpose system. Then the next question is why we want to use matrix algebra. It actually can simplify most mathematical expressions and computations significantly. With matrix algebra, you don't need to define tons of variables or do the calculation for each one. You just need to focus on the concept involved and understand where your results come from. In the matrix algebra, there are some fundamental definitions. The first one is scalar. It usually represents a number. The second one is a vector. It represents a single row or column of numbers. Usually it's denoted with both small letters. In this page, the letter A is defined as a row vector and the letter B is defined as a column vector. A matrix is defined as an array of numbers. Here, capital A, which will include 6 elements A11, A12, A13, second row A21, A22, and A23. In general, a matrix is denoted with both capital letters. Also, for all the matrices, they have an order, or we call them dimensions, usually represents the number of the rows times the number of the columns. For the example, capital A here is defined as 2 by 3 matrix. Another specific matrix, which is called a square matrix, is a matrix that has the same number of rows and columns, that is n by n. There are 4 fundamental matrix operations: transposition, addition and subtraction, multiplication, and inversion. The transpose of a matrix is a new matrix that is formed by interchanging the rows and columns. In general, the transpose of A is denoted by A prime or A capital T. For example, if we have the matrix capital A with a dimension of 3 by 2, then the transpose of A, that is A prime, will become a 2 by 3 matrix. If we have A equals A prime, then we say that A is symmetric. We can introduce addition and subtraction operations for any two matrices, but these operations can be done if and only if the two matrices have the same dimension. To complete these operations, you just simply add or subtract the corresponding elements. For example, for the addition of two matrices A and B, which have the dimension of 3 by 2, then the result, capital C, also has the dimension of 3 by 2. In this operation, C11 is just the addition of A11 and B11, and similarly for all the other elements. There are two types of the matrix multiplications. The first one, to multiply a scalar times a matrix, we just simply multiply each element of the matrix by the scalar quantity. And the equation here shows how the operation is completed. Second one, to multiply a matrix times a matrix, then we have to consider the conformable conditions. Usually, this kind of multiplication can be written as A times B. In this condition, the number of the columns for the matrix A should be the same to the number of rows for the matrix B. The slides here shows how the multiplication can be completed for two matrices. The equation here shows the values of each element in the result matrix capital C is completed by the elements of the matrix A and matrix B. Here is one simple example of matrix multiplication. In this example, A is a 3 by 3, B is a 3 by 2. They will result in a 3 by 2 matrix capital C. The calculation of each element in C is shown below. For the first element, C11, it's determined by the first row of matrix A and first column of matrix B, which will give the result of 30. You can do the similar process for all the rest elements. There are some fundamental properties of matrix multiplication. First, A times B does not necessarily equal to B times A. For example, if A is 2 by 3 matrix and B is a 3 by 2 matrix, then A times B equals a matrix which is a 2 by 2, but for B times A, it will result to another matrix, capital D, which is a 3 by 3. The second one, the matrix multiplication is associative. So we will have A times the multiplication of B and C equals to the multiplication of A and B times C. And third, their multiplication and transposition. The transpose of A times B equals to transpose of B times transpose of A. There are some specific matrices. The first one is a diagonal matrix. A diagonal matrix is a square matrix that has values on the diagonal, with all off-diagonal entities be 0. The matrix here is one example of diagonal matrix. The second one is the identity matrix. It's also a diagonal matrix, but the diagonal elements are all equal to 1, which can be represented in this example. For any matrix, the multiplication between the matrix and the identity matrix, the result will be the same. That is A times I equals A. The third one is a null matrix, where all the elements in that matrix equals 0. And this is just one example of the null matrix. A matrix also has some characters. The first one is a determinant. Generally, the determinant of a matrix is denoted by absolute A, or we say that determinant A. The determinant exists only for square matrices. And it's really hard for us to calculate the determinant of the matrix. Usually, we will rely on some computation tools, such as Excel or MATLAB. But if for a simple low-dimension square matrix, such as a 2 by 2 matrix, we can calculate determinant as absolute A equals A11 times A22 minus A12 times A21. In these slides, I list some properties of determinants, and they are very useful for you to do the matrix operations. It will be better for you to remember all of them for the future studies. Another character of matrix is rank. It's defined as the number of linearly independent rows or the number of linearly independent columns. So here we should refer to the linearly independent characters. A set of vectors is said to be linearly independent if and only if we can find some scalars, say that from C1 to Cn, which can be applied for the elements in the vector A1 to An to make them be 0 in this formula. And the matrix A of dimension m by p is of rank p. If p is smaller than n, then we say that A has the maximum possible rank and is also to be defined as the full rank. In general, the maximum possible rank of n by p matrix is the minimum value of n and p. The last character I will show is the inverse of the matrix, which is also denoted as A over minus 1. A matrix has an inverse if and only if it's a square matrix. And if we say that matrix B is an inverse of matrix A, then A times B will be an identity matrix. And similarly, B times A is also an identity matrix. So we can say that A times B equals B times A. And a matrix which has an inverse is called a non-singular matrix. And a matrix which does not have an inverse is a singular matrix. Also, an inverse exists only if the determinant of the matrix is not 0. It also has some properties for the inverse of the matrix. First, the inverse of A times B equals to the inverse of B times inverse A. And the transpose of A inverse equals to A inverse transpose. And the inverse of inverse A equals to A. Now let's move to the second topic, calculus, which is also very important for the study in this class. In calculus, the most important concept is called a function, which is the mathematical relationship between two variables we define as input and output. So for each input x, it will relate to one and only one output y. With this property, we can ask one question. Does an arbitrary vertical line intersect with more than one place in the function? The answer is no, because for each input we can only find one output. That means only one point can intersect with one vertical line related to one input. If in the function it has small changes in x resulting in small changes in y, then we call the function as continuous function. The question is, can you draw the continuous function without lifting your pen from the paper? The answer is yes, because the whole function is continuous. There will be no holes or skips in the function, so you can continuously drawing the whole functions without lifting your pen. In calculus, we are always dealing with differentiable functions. And in general, a function is differentiable at a point when there is a defined derivative at a point. We also have a definition called continuously differentiable, which means the function is differentiable at every value of the input variable. If the function is differentiable, then it's always continuous. However, a continuous function is not necessary to be differentiable. And when the function is differentiable, we can use all the powers and features that we defined in calculus. So now we need to know what's derivative. The derivative of the function is the rate of change of the function. So the derivative at a particular point of the function can be interpreted as the slope of the tangent line at that point of the function. So it will show that if there are small changes in the input variable x, how much changes can be applied to the output y. If the function is a linear function, then the derivative is constant, which is the slope of the line. For example, if we have the function y equals m times the input variable x plus b, then the derivative of y over x at little m. For linear functions, the derivative is always constant, but for nonlinear functions, the derivative is not constant, but rather is a function of the input variable x. For the function with only one input variable, there are some fundamental rules of derivations, including power rule, derivative of a constant, chain rule, product rule, quotient rule, and addition rule. I believe you all have learned these rules in calculus, so I will not touch in the details in this lecture. In the previous example, we only applied the derivative for the function once, but in calculus, there are also some higher derivatives, which means we can introduce differentiation operations for the function more than one time. For some functions, such as polynomial without a factorial or negative exponent, the function will eventually reduce to zero. But for other functions, such as the exponential function, it cannot reduce to zero. In calculus, we use exponents and log algorithms a lot. The log is actually very useful for understanding exponential growth and decay. Log is actually the inverse of exponentials. So if y equals b over x, then log by equals x. In practice, we often use the base e, which is the Euler number. So the log x, which would be log ex. Or sometimes we also use the base 10. Here are some fundamental rules for log algorithms, and it's very useful for you to do the operations with log and exponential. I believe you also see these rules in the calculus, so please recall all those rules for the future study. The derivative of log is also very useful in the whole calculus. In general, the derivative of log x equals 1 over x. Then, to solve the derivative of log 2x, you can either use the chain rule plus the fact that the derivative of log x equals 1 over x, or use the fact that log 2x equals log 2 plus log x, and find the derivative of each term. And in general, the derivative of log kx is always equal to 1 over x. Also, for the derivative of log gx, you can always use the chain rule to find out the solution. The derivative of exponent is very unique. Actually, the derivative of one exponent is just itself. To solve the derivative of e2x, you can apply the chain rule, and the formula here shows the process for you to using the chain rule to find out the result. In general, the derivative of e2x equals 2 times e2x. Previously, we showed the derivative of the function with only one variable, but in all the studies in this class, we are also talking about some functions with more than one variables, which we call as multivariate relationship. For example, the demand for the energy efficiency appliance depends on the income and the price, and the growth of the prey population depends on the natural production rate, the rate of the growth of predator population, the environmental carrying capacity for prey. In this sense, the partial derivative is very important for us to understand the relationship between the input variables and the output. With the partial derivative, we can express the change in the output variable given a small change in the input variable, with other variables still in the mix. Then we can learn how to do the partial derivative. Actually, the first thing we will do is distinguish a function into multiple terms, and then we will use the addition rule for derivative to distinguish each term. And we will differentiate each term one by one. For example, if we are differentiating with respect to x, and if the term has x in it, then we take the derivative with respect to x. If it does not have x in it, then it's constant to x, and the result is 0. We also can define cross-partial derivative for multiple variables. Say a function f has two variables x and y. Then we first do derivative to x and then to y, or we can do the other way around, which will give you the same result. The total derivative represents the change in a multivariate function with respect to all variables. It's just the sum of the partial derivatives for each variable multiplied by the changes in that variable. Another important operation in calculus is the integration. The integral of the function is actually the area under the curve or the line. It's the reverse operation of differentiation. For example, the integration of the derivative of function to x with respect to x is fx plus a constant variable. The integration is useful for recovering total functions when we start with a function representing a change in something. So that means two functions that have the same derivative can vary by a constant. For example, the derivative of x squared plus 300 is 2x. The derivative of x squared minus 500 is also 2x. With integration of 2x, we can get x squared plus a constant term little c, which can represent the two functions we listed here. There are some fundamental rules of integration which are very useful for you to complete the integration operations. And still, I believe you all learned all those rules, so I will skip the details in this lecture. The whole calculus is very useful for us to solve optimization problems. We can use the first derivative to characterize how the function is changing over the input variable. If dy over dx is positive, then the function is increasing over the input variable x. If it's negative, then it's decreasing. At the point of 0, it has two meanings. It could be the critical point where the function is not increasing or decreasing, or the inflection point. We will go to the definitions of these two types later. Regarding to the optimization problem, which we want to find out the maximum or minimum on the function, we will first take the first derivative, find where the first derivative equals 0, which is the critical point for minimum or maximum. Then we will take the second derivative, and the second derivative will characterize how the changes is applied at the critical point. At the minimum, which means the first derivative is 0 and the second derivative is positive. At the maximum, the first derivative is 0 and the second derivative is negative. Remember that the condition of the first derivative equaling 0 is a necessary condition for minimum or maximum. The positive secondary derivative is just a sufficient condition for minimum, and positive secondary derivative is a sufficient condition for maximum. They are not necessary conditions. Now we will see how to define inflection points. The inflection point is where the function changes from concave to convex or vice versa. We can use the second derivative to identify the inflection point. In general, at the inflection point, the first derivative is 0 and the second derivative is also 0. But you should remember that the second derivative is 0 is just a necessary condition, but not a sufficient condition for inflection point. So the inflection point is where the first derivative is 0, but the point is not a minimum or a maximum. It's just the point where the function will change the concavity. Now let's move to the third topic, probability and statistics. In this topic, the most important concept is the random variable. And the first type of the random variable is the discrete random variable. A variable x, if it can take at the most a countable number of values x1, x2 till xn, then we say that x is a discrete random variable. With discrete random variable, we can define a probability mass function, little px. Little pxi is defined as probability that the variable equals to a value xi. And if we sum the probability of all the possible numbers, then the total value should be 0. We also can define the distribution function capital Fx as the probability that the variable is less than little x, and the value can be varied from -infinity to infinity. This slide shows one example of discrete random variable. Considering one demand size random variable takes the value of 1, 2, 3, and 4 with the probability of 1, 6, 1/3, 1/3, and 1, 6. And the probability mass function can be represented in the figure on the left, which will have the probability for each value. And the figure on the right shows the cumulative distribution function, and you can find that the probability increased from 0 to 1. Another type of random variable is a continuous random variable. With this random variable, there exists a non-negative function fx, which is the probability density function, which we also call the PDF. It can make sure that at any set of real number, capital B, the probability of the variable x in that set is the integration of fx in the set B. And we also have one condition for the PDF. The integration of fx from -infinity to infinity is always 1. And if x is a number and delta x is positive, then we can find that the probability that the random variable between x and x plus delta x equals integration from x to x plus delta x for the PDF. And that's just the areas covered by the probability density function. The cumulative distribution function capital Fx for a continuous random variable x is similar to the discrete random variable. It's defined as probability that the variable is less than one value x, which equals to the integration of the PDF from -infinity to the value of x. Here is one example of the exponential random variable with the mean of beta, and the probability density function equals 1 over beta times exponential minus x over beta. Here x is the random variable. And the figure below shows the PDF under different x values, and we can see that the probability is decreasing over the value of little x. And this figure shows the cumulative distribution function of the exponential random variable. And based on the definition of the cumulative distribution function, we can find that capital Fx equals 1 minus exponential minus x over beta. And similar to our previous example, the value increased from 0 to 1. And that means capital F infinity is always 1 based on the definition of random variable. There are some features of random variable we have to define. The first one is the mean or expectation, which we are trying to find the expected value of a random variable. It's usually denoted by mu or ex. If x is a discrete random variable, we will use the sum operation to identify the expected value. If x is continuous, we will use integration to estimate the expected value. The mean is one measurement to identify the central tendency of the random variable. There are some features for the variable means. First, if the little c is a constant term, then the expectation of cx equals to c times the expectation of x. And second, the sum of two random variables x plus y, their expectation equals to the expectation of x plus the expectation of y. Another important feature of a random variable is variance, which is usually denoted by sigma square of variance of capital X. The formula here defines the way for us to calculate the variance. It is the expectation of x minus mu square or similarly expected x squared minus mu squared. The variance is the measure of the dispersion of the random variable about its mean. So the figure here can show you the impact of the variance. For two similar random variables with similar probability density functions, the one with larger variance will be flatter, but the one with a smaller variance will be more concentrated. Also, there are some features of the variance. First, for the variable c times capital X, if little c is the constant term, then the variance of this term equals to c squared times the variance of x. Second, for the sum of two random variables, x plus y, if x and y are independent, then the variance of x plus y equals variance x plus variance y. Additionally, the square root of the variance is usually called the standard deviation and is noted as sigma. The figure here shows one typical normal distribution with the mean of mu and the variance of sigma squared. In general, the areas under the region mu minus sigma to mu plus sigma is about 0.68. The third feature of random variables is covariance, which is applied to measure the relationship between two variables. The covariance between x and y is defined as covariance of xy, which is the expectation of x minus ex times y minus ey. It's also the same to expectation of x times y minus expectation of x times the expectation of y. The variable is applied to measure the dependency between x and y. And if x equals y, which means the covariance of x and x, it will equivalent to the variance of x. In addition, for the value of covariance x and y, if it's 0, which means x and y are totally independent. If it's positive, means x and y are positively correlated. If it's negative, means they are negatively correlated. Now we can summarize some interesting features. In general, for any two random variables, x and y, the variance of x minus y equals to the variance of x plus the variance of y minus 2 times the covariance of x and y. If x and y are independent, then we know that the covariance of xy is 0, which means the variance of x minus y equals variance of x plus variance of y. And also, we can define the correlation between any two random variables, x and y. The correlation of x and y equals the covariance of x and y divided by the square root of the variance x times variance y. And it will give us the value like the correlation of x and y is always between -1 and 1. With random variable, we can then define stochastic process, which is the collection of similar random variables ordered over time, and they all defined relative to the same experiment. If the collection is x1, x2, x3 till xn, then we have a discrete time stochastic process. If it's continuous over the time, like xt for any t greater than 0, then we have a continuous time stochastic process. Now let's see one example of stochastic process. Considering the single server queuing system with independent inter-arrival time of tasks, we have A1, A2, A3 till AN, and the independent processing time for each task as P1, P2 till Pn. Then relative to the experiment of generating AIs and PIs, we can also define the processing delay time in the queue as D1, D2 till Dn. In this example, we can claim that A1, A2 till AN is in the set of stochastic process, and P1, P2 to Pn is another set of stochastic process. For the delay, we know d1 is 0, but for the other d's, di plus 1 is the maximum value of di plus pi minus ai plus 1 and 0. And here we can claim that d is also in a discrete time stochastic process. The stochastic process is usually applied for us to identify the features of some random variables. For example, we can use the stochastic process to estimate the means and variance. Assume that we have n random variables which comes from the same experiment x1, x2 to xn, and they are independent and identically distributed, which means they will have the same population means and variance, which are defined as mu and sigma square. Then for the mean of the random variable x bar n, it's defined as the average value of the n experimented result. And the variance is defined as s square n, which will be represented in the formula here. Please note that the dimension here is n minus 1. Also, we can find out the variance of unbiased estimator x bar. In this stochastic process, the variance of x bar square equals to sigma square over n, but the estimated variance of the x bar is s square n over n. Well, the previous formula just shows how we can estimate the x bar, but we still don't know how the value of x bar is close to the actual mean of mu for the whole population. Then to assess the precision of x bar, we need to construct a confidence interval for the true expected value mu. The confidence interval could be identified by the following equation. First, if we know that there are n IID random variable x1, x2 till xn with the same mean mu, then we can construct 100 times 1 minus alpha % confidence interval for mu, which will be x bar plus minus t times the square root of s square over n. Here t is in the upper of 1 minus alpha over 2 critical points for a t distribution with the degree of freedom of n minus 1. This figure shows the t distribution with n minus 1 degree of freedom. It represents as the red line, and the green line shows one standard normal distribution. We can see that the t distribution is very similar to standard normal distribution, but it's still a little bit different. We will use this one to identify the confidence interval from the stochastic process. When we constructing the 100 times 1 minus alpha confidence interval for the random variable through the stochastic process, if the number of variables is large enough, which means n is sufficiently large, then the portion of the confidence interval that contains mu should be close to 1 minus alpha. Alternatively, if n is the normal distribution with the mean of mu and the variance of sigma square, then the coverage of probability will always be 1 minus alpha regardless of the value of n. But if x is not a normal distribution with mu and sigma square, then there will be a degradation in coverage for small n, and with greater the skewness of the distribution of x, the greater the degradation will be. So in order for us to get an accurate estimation about the confidence interval, we need to select large enough value of n for the stochastic process. This is the end of the lecture today. Thank you very much for listening. The slides are shared with you through the email. In the email, I also share one file about advanced probability and statistics, which are highly related to the first homework. Please go through the file and also the slides carefully.